I'm Anil Kumar. Welcome to my series on graphs. In this video, we'll discuss the role of derivatives to analyze turning points. They really help you to sketch a very accurate graph. We'll look into turning points from equations. Here's a statement which says true or false. Gradient equals to 0 implies turning points. We'll discuss that. Gradient test for local extrema. That is to say, if we know that there is a turning point, it could be a local maximum or local minimum. How do we analyze and figure out whether it is local maximum or minimum using the first derivative, which is the first derivative is the gradient, right? We can also use the second derivative to find the type of extrema. And we're going to take a very simple example, f of x equals to x cubed minus 3x plus 4, to illustrate. So let's begin with a simple graph first. Now, from a graph, it is very easy to figure out about the turning points, right? Let's say this is the graph given to us. Now, from here, we know very clearly that we have two turning points. So here we have a turning point, let's say turning point 1, right? So that is one turning point. The other turning point is right there. So that is a second turning point. And from the graph, we can also say that this turning point is a local maxima, right? So we have a local maxima here. So L and maxima in short, I'm writing as max. And in this case, we have a local minimum. What you also observe here is that if I draw a tangent at this point, it will be horizontal, correct? So at both the points, what we conclude here is that the gradient, that is slope of tangent, is equal to 0. So that is what we conclude right there. So if the gradient slope of tangent is 0, then we have a turning point, and that really gives you the turning point. Is that clear to you? So how do we find the gradient? Well, clearly the gradient is the first derivative, right? So what we say here is that the first derivative which is written as f dash x equals to 0. If that is true, then we say turning point is possible. Well, I wrote the word possible here. Means sometimes we may not have a turning point, right? So what we actually call this first derivative equals to 0 is a critical number. So we actually get this as a turning point possibly, right? So what we normally call this, we say this is a critical number. So let me define another term here, critical number. So critical number is the value of x for which first derivative is equal to 0 or first derivative is not defined. We normally say does not exist, right? So if the first derivative is 0 or if it does not exist, in that case we have a critical number. And a critical number is a possibility of turning point. So from here we can say that at both the points we need to analyze critical number for turning point, right? Now when we analyze the critical number for turning point, we are only looking into the first part, That is to say that the first derivative is 0, right? But critical number also is a point where the first derivative is not defined, right? So both are the cases. In polynomials, it will be normally 0, right? But that also will be a possibility which we'll take up in other examples, right? Okay. So what we understand here is that from graph it is easy to remember, to check where is the turning point, but from the equation we could figure out if we find the first derivative, correct? So let's move forward and check where do we have turning points from the given equation. So now in this part of the video we will understand how to find turning point from the equation. So we are given the function f of x as equal to x cubed minus 3x plus 4. The first derivative of this particular function is 3x squared minus 3. To find the critical number, what we need to do is to equate this derivative to 0 or does not exist. In this case, it is a continuous function. It exists at all the points of x, and so let's figure out when it is 0. So we can write 0 equals to 3x squared minus 3 to calculate the value. So that gives you 3 is common. We get x squared minus 1, which can also be factored, and you could write this as x plus 1 times x minus 1. So clearly we get our critical numbers. So we have two critical numbers. So we have possibility of turning point at x equals to minus 1 and at x equals to plus 1. Do you see that? So in this case, we do have a possibility at both these points. We can actually find the value of the function f at both these points. So at minus 1, the value is minus 1 cubed minus 3 times minus 1 plus 4, which is minus 1, that is plus 3 plus 4. 7 minus 1 is 6. And the value at 1 will be 1 cubed minus 3 times 1 plus 4, which is 1 minus 3 plus 4. So 5 minus 3 is 2. So we do have 2 points here. So our points of interest are at x equals to minus 1, the y value is 6, and at x equals to 1, the y value is 2. Now, are they the turning points or not? Most of the time, whenever we have the first gradient as 0, we normally get a turning point. But there are possibilities that it may not be a turning point, right? So we'll keep it as such at present. But it is one thing is very clear, and that is that at turning point, we have either a local maximum or we have a local minimum, right? So if we really find or analyze the turning point for local maximum minimum, we'll know exactly whether it is really a turning point or not and what does that turning point implies, right? So we're actually hinting at the second question, right, which is the statement which says true or false. Gradient equal to 0 implies turning point. Well, here is an exception which will help you understand why we are not concluding to this decision. If I take the function f of x equals to x cubed, then the derivative of this function will be 3x squared, right? Now, for this particular function, we do not have any turning point. At x equals to 0, no turning point. The question is why? Well, if you sketch this graph x cube, it may look like this. So that is the graph of x cube. As you can clearly see here, that at 0, it doesn't really turn. It moves as such. So we have to be slightly more careful while concluding after this particular test, gradient equals to 0, whether it is a turning point or not. And since we are also looking into local maximum and minimum, we'll actually move forward and do this conclusion after testing our turning point. Is that clear to you? Right? So remember that always when we have a critical number, then it is not necessary to have a turning point, right? We could have what we call here as point of inflection. Correct? So we could have a point of inflection. Perfect. So let's move forward, analyze our critical number, and then conclude about the turning point. So now let's move forward, analyze the critical number, and then conclude about the turning points. So once again, we have the same equation to work with, and we'll perform the gradient test to figure out whether we have a local maximum or minimum at our turning points or not, right? So what we did so far was that we found the derivative of this function x cubed minus 3x plus 4. The derivative of this function was 3x squared minus 3. So this derivative gave us two turning points. I mean, we have not really concluded that. But we say, well, the turning points could be at plus and minus 1, right? So I could write this as 3 times x plus 1 times x minus 1. So we expect two turning points. Now, with the help of gradient test, we'll first figure out whether we have a local maximum or local minimum at these turning points or not. If they are turning points, we'll have local maximum and local minimum. Is that clear to you? Right? Okay. So the test is as follows. What we are going to do here is we'll analyze the points near the critical numbers. So here we have two critical numbers, right? So the critical numbers are x equals to minus 1 and x equals to plus 1, right? So we are going to analyze these two critical numbers. So let us say that is our number line. We have x equals to minus 1, x equals to plus 1. So what we do here is that we take test points in these intervals. Now these two critical numbers, they are actually dividing our plane into 3 intervals, right? So we have an interval from minus infinity to minus 1, from minus 1 to 1, and from 1 to infinity. So we take a test point in these. We prefer to take in between all the critical numbers. So in this region, we could take a point which is minus 2. Here 0 is a good point, 2 is a good point. Now, at these points, we analyze our factors, which is the first derivative. It has 3 different factors, so there is no harm in writing them separately, right? So what we will do here is we'll write them all separately. So first factor is 3, the second one is x plus 1, the third one is x minus 1. At the given points, we'll check if these are positive or negative, right? So that is the whole idea. 3 is going to be positive everywhere, just plus 3. When I substitute minus 2 here, we get negative. 0 will give us positive, 2 will give us positive. When I substitute minus 2 in the x minus 1 factor, we get negative. 0 will give us negative, and 2 will give us positive. Now when you multiply them all, you get your first derivative, f dash x, correct? So here we have two negatives and a positive, which will give us a positive. Two positive and negative will give us a negative. All positive will give us positive when you multiply. Positive means what? Well, positive means that the gradient is increasing. So that means the function is increasing, right? Negative means function is decreasing. Positive means function is decreasing. We are talking now about the function f of x. So in this interval, the function is increasing and then decreasing, and then it is decreasing and then increasing. So that clearly means that we have a turning point. So that means we have a turning point here and we have a turning point there also. Do you see that part? So now we conclude that we have two turning points. So we have two turning points. And these turning points are at minus 1 and at plus 1. We calculated at minus 1, we got a value which was 7 minus 1, which was 6, and at plus 1, which was 5 minus 3 as 2. So those were our points, turning points. Now, from the first derivative test, we'll conclude whether it's local maximum or local minimum. Now clearly, as you can see from here, the function gradient is increasing then decreasing. That means we have reached a maximum. So this is called local maximum. And here the gradient is going down then increases. So that means we have hit a bottom value, the minimum value. So this is local minimum. Is that clear to you, right? So from here, we conclude that from the gradient test, we see that the first derivative changes from positive to negative, right? So when it does so, when it changes from positive to negative, then the gradient changes from this, then the function has local maxima. So in our case, it is at minus 1, 6. Perfect. And when the gradient changes from, so when the gradient changes from negative to positive, in that case, the function f of x has local minimum. In our case, it is at 1 and 2. Correct? Do you understand? So basically, we can roughly sketch our graph, which is we have a maximum at minus 1, right? So we have a graph which is kind of like this. So I'm not making a scale here. However, we are working on this. So this point, which is at minus 1, 6, is our local maximum, and the other point, 1, 2, is our local minimum. And both are the turning points. Is that clear to you? So we have two turning points, right? So we have two turning points. One of them is a local maximum, the other one is a local minimum. And we did the gradient test, or sometimes we also call the first derivative test, right? So let me write down here. It's also called first derivative test for local maximum or minimum. Is that clear to you, right? So I hope this test is absolutely clear. Now, you also observe here that the graph has concavity. So this is concave down, that is concave up. So concavity also gives you a way of verifying whether we have a local maximum or minimum. So next, we'll now take up the second test, which is to check concavity. Perfect. So you saw how we figured out that we have two turning points for the given example. We have also analyzed which one is local maximum, which one is local minimum. However, there is another test, which is second derivative test, which can also be applied to find out which turning point leads to local maximum and which turning point leads to local minimum, right? So we are now going to check concavity using second derivative, right? So let's figure out what is the second derivative. The function given to us is x cubed minus 3x plus 4. The first derivative of this function is 3x squared minus 3. The second derivative for this function is 6x, right? Now, we already found that the critical numbers for this are what? Let me write down. So let's find the critical numbers. So critical numbers basically are numbers where the first derivative is either equal to 0 or it does not exist, right? So both are critical numbers. In our case, we have the first derivative as 3 times, we'll just factor this out, x squared minus 1. So this leads to x equals to plus minus 1 as critical numbers. So we are trying to analyze the critical numbers and verify whether the turning points or the critical numbers lead to local maximum or local minimum, right? So if I do the second derivative test, that is to say, at the first critical number x equals to minus 1, let me write down here. So if I substitute x equals to minus 1, in that case, what do I get? The second derivative is 6 times minus 1, which is minus 6. Now clearly, this minus 6 is less than 0. Now if the second derivative is less than 0, then we can say the concavity is concave down. Then we can say that the graph is concave down. So that leads to concave down function f of x. So if the function is concave down, what do we have here? We have a local maximum. Is that clear to you? So it's very fast. You see, we found the first derivative and the second derivative. First derivative, we got two values. So when we equate this to 0, we get two values. And those are x equals to plus 1 and x equals to minus 1. And substituting those values in the second derivative, we immediately get our result. So if I substitute the second value, which is plus 1, I get 6 times 1, which is plus 6. Now plus 6 is greater than 0. That means the concavity is kind of like this. You can hold something, right? Greater than 0 means positive, right? You can hold something. This is negative, right? Now that means the graph is concave up. So this is concave up graph of function we are talking about, right? So in the function, what we have here is a local minimum. So we have local minimum at x equals to 1. The value which we figured out was, if I write 1 here in the function, 5 minus 3 is 2. So that becomes the local minimum. We can write here, right? So local minimum is 1, 2, and the local maximum which we got is at minus 1, and what? 7 minus 1, 6. So that is how very easily with second derivative we can figure out whether the graph has a local maximum or local minimum at the turning point. Perfect. So I hope that helps. Now this particular exercise which we did is also very important for sketching very accurate graphs. So what question you have now is, question for you is sketch graph of the function f of x equals to x cubed minus 3x plus 4, correct? You know more or less how it looks like, but substitute your values and get an accurate graph. I hope that helps. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.